introduction.
Hi, it's my pleasure to introduce our speaker, Rob Pinkel. Rob is a professor at Scripps Institution of Oceanography and Associate Director of Marine Physical Laboratory. His education includes a Bachelor in Physics from University of Michigan and both Master's and PhD from Scripps Institution of Oceanography. Rob's interests include energy cascade in the ocean, internal waves, and ocean mixing, both Arctic and tropical oceanography, and also observation techniques and instrumentation. Rob is a recipient both of Mank Award and Stommel Award. He will talk today about Tasman Tidal Dissipation experiment. So we are welcome, Rob, and we are ready.
Well, thank you, Maria. I'm hoping folks can hear me, and I'm excited to talk today about this experiment, TTide, Tasman Tidal Dissipation experiment, that has been going on for the last number of years and is now in some financial way winding down, but the science is just beginning. It's an interesting thing for me to present to you as a panel, in that I'm not entirely sure I'll be telling you what you're most anxious to learn. So hopefully Maria or someone else can intervene if I get too much into the science background of things and turn this into a science talk rather than into something you're directly interested in. But let me know if that's going on, and meanwhile I'll just blunder along. It's my sense that, as climate modelers, what one wants out of a bunch of measurements of turbulence and dissipation in the ocean is a sense of an eddy diffusivity that can be applied to both the density field and scalars and maybe the velocity field. And what one would love to get out is a parameterization for an eddy diffusivity that has both space, time, and physical parameters in it, so that you not only get a diffusivity that applies at climatological scales, but whatever model of diffusivity you get is able to adjust and change itself as the climate changes. And this is a kind of a challenging thing to come up with, given the fact that the basic phenomena that are involved in establishing this just diffusivity in the deeper parts of the ocean are just being identified right now. Let me hit the second point. Getting global parameterization from a very few number of process experiments is quite a challenge. There are things that we'll be talking about today, like near bottom bores, lee waves, and so on, that have a very distinct nonlinear life of their own. And to talk about a climatologically relevant eddy diffusivity is to be able to say you understand the climatology of all of these small-scale, weird, nonlinear things. And so that's kind of what TTide is trying to get at. And if you think of a climate model, it's often expeditious to prescribe some sort of an eddy diffusivity where it's needed and adjust it to make the model behave. But as you turn an eddy diffusivity up and down, and if you think of a buoyancy flux, say, roughly 5 times the amount of power is dissipated as goes into the buoyancy flux. And if it takes a couple of terawatts to maintain a diffusivity that's consistent with reality, it's important to have some sort of a mental image of how that energy is being delivered into your climate model in a consistent way. And today we'll be talking about tidally driven mixing, and the tides are probably absent in climate models. So whatever tidal dissipation is coming in, it's kind of free energy from the perspective of a climate model. But if you think of the Pleistocene and sea level fluctuations, when the continental shelves of the world come out of the water at the height of a glacial period, there's going to be roughly 5 times as much tidal energy available for dissipating, for mixing the deep sea. and the parameterizations have to kind of be aware of that, and we'll have to understand the role of tidal mixing versus other mixing processes. If all of the energy involved in mixing the ocean comes through a cascade of the general circulation to the mesoscale, to the submesoscale, things that are supposedly in a climate model, then that energy is in the system already and available to be used. If, for example, a lot of the mixing of the deep sea comes from energy that's associated with near inertial waves that propagate down into the sea and break, then the energy, a terawatt that's going into driving the near inertial waves, can't also be used to drive the general circulation. And so you have to be aware of all of this stuff in thinking about diffusivity. It makes for an interesting time right now because these problems are no longer impossible. They're really quite close to being tractable. The most tractable thing is understanding the energy source associated with the surface tides to the internal tides to breaking internal tides and so on. And there's been enormous progress in this in the last 20 years. And to me, a lot of this progress is symbolized by maps such as this one that Harper Simmons made probably 12 years ago or so now. And he's been refining these ever since. This is a map of the Pacific, of course, and the little reds and blues are crests and troughs of a baroclinic first mode tide that is generated as the barotropic tides flow over topography. And what you can see is there's a very distinct pattern of tidal beams reaching out across the Pacific in his numerical model. And the pattern is based both on the barotropic tides and on the idiosyncrasies of the topography of the Pacific Ocean relative to the stratification, which sets up how good a generator the different topographic things are. And the surprising thing is that there seems to be an enormous amount of reality associated with maps like this, and we're learning how much to trust them as time goes on. You can see initially at the turn of this millennium, we started studying the tidal generation conversion site off of Hawaii, and one of the lessons learned was that even though there's an enormous amount of energy extracted from the barotropic tides and a lot of dissipation right locally around the topography, most of the power, most of the energy that's coming out of the barotropic tides ends up radiating out across the Pacific in the form of a mode 1 baroclinic tide. So about 80 to 90% of the energy escapes. And in terms of mixing the deep sea, we have to understand what the fate is of that energy as it heads out across the Pacific. Around 10 years ago or so, Jen McKinnon and Matthew Alford led a project to try to sail the ship and put moorings right down one of these tidal beams as it headed north to the Aleutians. And what was found was that there was a lot less dissipation on the tidal beam, along the beam, than there might have been, and it didn't seem like it was dissipating catastrophically fast. And that raised the issue of where does this dissipation ultimately occur? And the thought was that it occurs when that beam intersects some abrupt topography. And at the time of these experiments that Matthew and Jen led, this map from Harper was just coming out. And it was very hard not to be attracted to this beam of energy generated at the Macquarie Ridge south of New Zealand, which was heading off toward the island of Tasmania. And this, of course, is a really great tidal beam in a numerical model. And the question is whether it was real. But it looked like an opportunity to do a real physics experiment where you take a beam of energy directed at a scattering target, take a look at the aftermath of the impact and see what sort of dissipation occurs, reflection, and what smaller scale scattering products like high mode waves and so on occurred at the site. And about 9 years ago now, we set up a plan that eventually became TTide to investigate this whole class of phenomena. I want to make the point today that the committee is set up to discuss process experiments and how the process experiment transitions to develop a numerical side and to benefit long-term climate modeling. But TTide ended up being a phenomenally cyborg experiment where it had both ongoing modeling and ongoing experimental sides that were both continually evolving. And the products from this experiment that you might be most interested in are the products probably of high resolution runs around topography on the Tasman slope that could be extended to runs around topography all over the world, rather than the output of some thermometer on a mooring line, which is indeed eventually going to end up in an archive, but will be out of context, not as useful. As things progressed, we looked closer and closer with the numerical models. Harper here has focused his gold model down to just look at the Tasman Sea, and on the left you see this beam of energy that's generated from the McCurry Ridge, which turns out when one looks close is both a ridge and then there's a little valley and then there's a plateau up behind it. And the interaction between these two things generates a very good tidal beam that is heading westward and northward toward Tasmania. And it's propagating through a very energetic mesoscale field here, the Tasman Sea, associated with the East Australia Current. And at this point, that mesoscale field wasn't in the model at all, and you've got this nice beam heading across. When you look closer at the island of Tasmania here on the right, the nice simple picture starts to get fuzzier and murkier. There's a large topographic feature here, the East Tasman Rise. And the tidal beam is clearly affected by this, and it starts to get murky in the numerical model what is happening to it. And these are all advances going on in the numerical model long before we put anything in the water to look. Harper made this great simulation where he sent just a couple of crests of a tide in to the coast of Tasmania and bounced them off the coast to see in his model how much the parameterized dissipation was killing the waves and how much might reflect. And what you can see in this, if you look, the contours of the continental slope and the south side of Tasmania are extremely steep. This is nearly a vertical wall, and by steep I mean steep relative to the slope of a tidal ray. This is a highly reflective area, and you can see the waves coming in, kind of refracting a bit around the East Tasman Rise and bouncing off. In the northern part of the island, the continental slope is very near parallel to the slope of a tidal ray, and this is likely to lead to a lot more dissipation. And so in this model, you can see the energy wrapping around and reflecting from the south, but very little reflecting from this region up in the north. And so this inspired the design of an experiment where we were going to attempt to compare and contrast the highly dissipative region we thought would be in the north with a highly reflective region further down in the south. We'd look for what sort of phenomena were going on at each of these places. Now again, long before we did anything in the water, modeling was started to look at what the slopes of Tasmania might be doing in detail. And Jody Climax fired up the MIT GCM to do this and to see what sort of nonlinear phenomena might be showing up associated with this impact of the incoming tide and the potential reflection. And his pictures were kind of sobering to us. In the top, what we're seeing is a slice of velocity, but the contour lines are density surfaces. And you can see down near the bottom, but lifted up off the bottom, they're vertical walls of water, bore-like things that are in midwater, where you might have a 100-meter tall vertical wall propagating up and down the slope. Also, where there's very little lumps like this little seamount here, you can get lee wave-like features happening that lead to a lot of dissipation very, very locally. It's clear if you wanted to understand how much mixing was going on, you had to do an experiment which both extended way up into the water column, at least 500 meters, and also at the same time track dissipation very near the bottom and with fine scale, less than 100 meters off the bottom, 500 to 1,000 to 2,000 meters down in the sea. So it ended up, as we progressed with the planning, looking like a more and more difficult thing to try to tackle. And as Jody moved these MIT numerical studies into 3D and could process the entire east coast of Tasmania with a hypothesized incoming tide, things looked even more sketchy in the sense that the dissipation was incredibly concentrated along discrete features that just happened to be nicely tuned to the geometry of baroclinic waves being forced at tidal frequency. Down in the south, where it was supposed to be very reflective, there is this geographic oddity of a whole bunch of vertical ridges that cut through the continental slope, going down to really quite great depths. And in these ridges, the model was detecting a certain amount of dissipation, indicated by this red color. Other odd lumps and bumps showed lots of dissipation, while similar-looking lumps and bumps didn't at all. And up in the north, which was supposed to be highly dissipative because this general slope is much flatter up here, much more parallel to a tidal ray, there's this odd lump, which we now call Climax Rise, much to Jody's disgust, that had most of the dissipation that was going on in the northern region. And then inshore, where you got into the upper part of the continental slope just before you hit the shelf, another spot of high dissipation. And so it's clear that as the stratification of the Tasman Sea changes with time, these different features come in and out of being tuned to be highly dissipative. And it seemed the appropriate thing to do is concentrate resources on this region up here with these highly dissipative geographic features and compare and contrast them with the supposedly reflective wall where dissipation was going on associated with these small ridges. So what came out of this was an experiment that went on over a 4-year period. It's just the antithesis of starting with the field phase and then moving on to the modeling phase, as has been done in generations of ONR sorts of experiments up until recently. But we started out first trying to identify whether Harper's incoming tidal beam in the model was actually real, and trying to use the topographic satellites to identify the tidal beam coming in. And Zhongzheng Zhao and Matthew Alford then at UW were looking at that. And in tandem, Jody Climax with his MIT GCM focusing on the Tasman Shelf and working outward, and Harper Simmons and his student Dmitry Brezhnikov focusing on the whole world and working inward, were trying to model what might be going on. We were somewhat desperate for in situ verification that anything was happening at all, and what there was were gliders that could be applied. And Sean Johnston and Dan Rudnick deployed some spray gliders from Tasmania to study what was going on in the Tasman Sea. And Robin Robertson and Luke Rainville looked at existing data from the Australian glider program. And it wasn't until 3 years into the program that any serious in situ physical oceanography was done. there was a single big process experiment with 3 legs, and on the first leg, a forest of moorings were put in to study the northern site and the southern site, contrast them, and then a separate set of moorings more outward into the center of the Tasman Sea to see how much energy might be reflecting. There was a second leg that I led that used an instrument we call the fast CTD to make deep density profiles and microstructure profiles to see if we could resolve what was mixing. And finally, in March of 2015, Matthew Alford went out again and did lowered ADCP microstructure surveys and then recovered this incredible forest of moorings that was deployed. In parallel with this, offshore in the center of the Tasman Sea, Amy Waterhouse and Sam Kelly got a separate program funded using the Schmidt Oceanographic Ocean Institute's Falcor and some NSF money that they achieved to do a series of stations in the central Tasman Sea to see if we could find in situ evidence for this tidal beam and quantify its strength to compare with what was modeled. And there was a second experiment done on the shelf inshore of the shoaling beam to see what the effect of all this mixing was on the shelf and how it might affect the fishery and local economics. And that was led by Nicole Jones of the University of West Australia and was funded by the Australian Research Council. And Drew Lucas at Scripps put a number of wire walkers out in support of that. And that was done from the U.S. perspective. It was a completely unfunded add-on. This is a picture of what is going on that is a little colorful. It's contoured on a background of total energy density. If one had a beam of energy coming into the Tasman coast and just dissipating here, the colors would all be uniform. And the fact that they start to look stripy is because standing waves are set up, and that occurs because the reflection is so strong. And if you think about it, physical oceanographers are good at measuring things like fluxes and phase propagation. And when you have standing waves set up, a lot of these tools don't work well. And so we had to figure out how to design an experiment that would provide useful information, either with propagating or standing modes, where you just get frozen patterns that don't change so much. In the end, efforts were concentrated along the slope in this northern array over the Climax Rise, down south where it was highly reflective, where these ridges were cutting into the coast. Then 3 moorings were put offshore where the reflection from the southern side of Tasmania should be heading out to sea. And we were trying to see how these moorings fit into the standing wave pattern, which would have a shifting phase if depending on the magnitude of the reflected versus incident wave. And way offshore, Amy Waterhouse and Sam Kelly were working to try to quantify the incident beam. So there's a lot of stuff going on in the 3-month period with 2 ships out there. And I'll go through a timeline of all of this at the end, because pictures like this make it sound like things were planned nicely, but we had a huge moving target all the time that this experiment was evolving, associated both with financial realities and the latest results of the modeling team and the latest results of the gliders and so on. Here's a photo of Sean Johnston's Spray glider and one of its paths up on the right. And at the end result of a whole bunch of glider runs and a lot of squiggly lines, Sean found that he could model the tide as an incoming plane wave and a reflected wave going out at a slightly different angle, and getting a total standing wave pattern that more or less paralleled the contours down in the southern part of the island. And his estimate was like 80 or 90% of the energy was reflecting down there, which was a sobering thing, because this was coming up as the field phase was designed and the arrays had to be designed to accommodate these sorts of results. This is a bit of a hard map to follow, but if you look closely, you're seeing the topography of the northern site here, where it's alternating steep, shallow topography. All of the moorings that were put in are these red dots, and we're trying to watch the tide as it shoals crossing Climax Rise, which is the little lump here that I'll come back to, and then the upper dissipation site that is in here. On the right is the much steeper topography of southern Tasmania, and all of these odd ridges, or valleys rather, are the things that were of interest in the MIT GCM, and we decided to instrument several of the valleys with moorings and then take and do lowered ADCP stations while folks were actually out there. An enormous amount of gear was involved in this. I'll have a list here in the next slide, and it's an incredible thing to make detailed plans to put in 15 moorings in the roaring 40s on schedule, in budget, and it all worked out thanks to the amazing efforts of Matthew Alford, Jonathan Nash, Jen McKinnon, and a large group. In the end, 3 moorings were put in for the reflection away, 1 way offshore to support the T-beam effort of looking at the incoming flux, 6 long-term temperature moorings, 8 McLean profiler moorings, and a bunch of other things involving hundreds of instruments, all of which, eventually have to show up in the archives. And I think any one of them, in absence of the pattern determined by the others, would not be of that great interest to the climate community. But in the long term, maybe the results of the MIT GCM, guided by these instruments or constrained by them, might be a really useful product to have. And the arrays consisted in the north of McLean moorings in black, and these highly instrumented 500-meter long thermistor chains that Jonathan Nash deployed to try to see bores and lee waves propagating along the topography in real time. If you look at a close-up of one of Jonathan's thermistor chains, I guess they're 300 meters tall, excuse me. This is a half a day, roughly, of thermistor chain output. And if we look at the black lines are isotherms, and in the lower picture, the contoured color is velocity. But what you can see is a band of red here of offshore velocity propagating downward from above. So the phase is going downward as if energy in these waves is going upward. And as the isopycnal surfaces get farther and further apart, the buoyancy frequency, n squared, is going down. And eventually things get jagged and you start to see what looks like turbulent motion in these things. And this is a pattern that goes on. And here's a pattern you can see isopycnals jumping up and suddenly being 100 meters higher than where they were just a few minutes before, as if bore-like things are indeed running along the bottom. So it's an incredibly cool data set. It's just now getting its due, getting looked at heavily, and we have several months of this, so it's pretty fun stuff. After this forest of moorings were deployed, the Leg 1 team went out and did lowered ADCP measurements with the ship's CTD, which was really challenged to work in the very rough conditions of the Tasman Sea. But they were able to see things bobbing the CTD up and down at about a meter a second that included vertical walls of water here, iso density lines that are just vertical, as bore-like things seem to be moving up the slope or perhaps down the slope. It's hard to tell just from this picture. But the virtue of the lowered ADCP was that there was indeed a Doppler sonar and ADCP on it, so they got velocity as well as as well as the density field doing this sort of thing. In leg 2, I was out with a conventional Seabird CTD that was packaged in the streamlined drop probe. And the thing is of interest in that, unlike going up and down at a meter a second, this one can profile near the surface at 5 meters a second vertically. So it's dropping and rising at 10 knots. And by the time you're 2 kilometers down, it's more like 4 or 5 knots rather than 10 because of the cable drag on it. But it's still a very quick instrument relative to the shipboard CTD. It has a little altimeter on it, an acoustic altimeter, so that we could turn the thing around 20 meters off the bottom, and some microstructure sensors up in the front. And this thing, if you look at 2 days, right on the top of Climax Rise, we had the ship parked in dynamic positioning, and you see a whole bunch of lines. Each kind of vertical blue line is another profile that happened about every 10 minutes. This is from 1,300 meters to 1,800 meters. So it's the sort of measurements that used to be made in the upper ocean, but now they're made right off the seafloor on the top of the rise, where the bottom is right at 1,800 meters. The horizontal wiggly lines are regions of high density gradient that are all crammed together, and you can track them coherently. And the red dots are regions of the water column where the water is overturning, where it's upside down, heavy water on top of light. And what you can kind of see is, again, these phase lines coming down with time, and as the isopycnals here dilate enough, n-squared drops, breaking starts kind of above the bottom and works its way down. There's no sign that this is frictionally driven in some bottom boundary layer. And you can even see some cool things like this is a tidal peak, and here's the next one. But in between, every 6 hours, the 6-hour harmonics coming down, and it's breaking too. So there's a lot of interesting stuff going on. And the tragedy of the experiment was that we had a few days at most at each one of a number of sites to try to figure all this stuff out. But these sites were chosen to be right near where the moorings were, and the hope is that by integrating the high-density measurements of the CTD with the moored measurements and the ADCPs that are on the seafloor, we can put a pretty good picture together. This is an attempt to do tow-yoing to actually make horizontal transects across right at the top of Climax Rise. We're going across this little bump there, back and forth. Each of these panels is only 8 kilometers across. Here's the topography of the seafloor. And on this particular transect, we ended up catching this nice vertical wall of water, a lee wave-like thing, with probably 100 meters of vertical drop to each of the isopycnal surfaces, or in this case, isothermal surfaces. The thing is that you see the isotherm sloping up, making the drop at the lee wave and continuing to slope up here. One of our problems was that the ship, as we were doing these CTDs, the CTD was moving up and down at 4 knots. The ship was moving across this field at 2 knots, and the tide itself was propagating on shore much faster than the ship was moving. So there's a mix of space and time all tangled together in these images, even though they are fairly high density in time as 1,500 meter deep images go. So what I tried to do was make a bunch of repeated passes across Climax Rise, back and forth with the ship. The red dots are when the CTD is coming up, the blue dots when it's going down, and we could merge those 2 data sets. And it's plotted versus the tidal phase, where the calendar time is just divided by 12.4 to wrap it around, and you can see what sort of coverage of tidal phase at each longitude we were able to get. And of course, it's really spotty with big holes here. The only excuse I have for leaving it like this is if you look at all these dots getting really close together, the weather was kicking up at this point, and The ship was going the same speed in terms of its propellers, but being literally blown backwards over the CTD in the headwinds here, and we eventually lost control of the ship at low speed and had to abort the series way early. But what I attempted to do with all of these things, at each longitude I would fit a sine wave in time at the tidal period, twice the tidal period, and 3 times the tidal period, and then turn this mix of back and forth trips into a movie, which hopefully will play. There it goes. And this is just a way of presenting this 3 days we saw. There's the lee wave breaking. And you can see when you actually see it break and then a harmonic break, that the actual isopycnal slopes are much flatter than when we did just the one transect where the tide was moving as fast as the ship, or even faster. So this is a movie that is not a numerical simulation. It's just a fit to data. There's nothing that wraps around in it except in time. It's going to repeat every 12.4 hours and give you that lee wave there. But it was a kick to try to do this, to really image what was going on here 1,500 to 1,900 meters below the surface of the sea. And you can see this big surge offshore that just happened near the bottom. It's almost looking like that there is a bore-like thing heading offshore that perhaps reflected out of the plane of our measurement line and is coming through it. There it goes, pushing offshore over the top. And that's kind of phased to kind of kick the lee wave off going the other way. So the tuning of this whole region is very complex, and it's something that a 3D run of the MIT GCM can handle much better than we can guess just from first principles. So it's really an interesting thing to try to bring the data up to the scale where it's relevant to the model, but we're having some success there. Let's see. If you go on here and look at how salinity and temperature might fluctuate on an isopycnal surface, what we have in the upper picture is salinity, absolute salinity, and how it changes with time on a density surface. So on the left, we don't have actually the depth scale, but it's actually the mean depth of an isopycnal that we're watching as it fluctuates. So the isopycnal is going up and down, and we're seeing the salinity decrease and then increase and so on as you go on in time. And what this picture is up the slope from Climax Rise, and what you see is quick changes in salinity that are happening over the course of a number of hours, way above the bottom here. And if you take temperature, in order to stay on an isopycnal, the temperature and the salinity map changes are identical one to the other with the exception of a scale. But what I've overlaid on this is where you see overturning and mixing, which is generally happening much deeper down in the image. And so what's probably going on is we're seeing the mixing products that were happening at a shallower depth inshore of us being washed out by us, while the active mixing that's going on down below us is not making giant instantaneous changes to the TS, but working a bit at a time. And it's fun to have diagnostic pictures like this because the whole game is to see how the mixing products are ventilated into the ocean interior. And here we're talking about 20 kilometers away from where this depth range was near the bottom. And so we're getting to see partially mixed shreds of water heading by us as we go. At any rate, let me summarize where we are at this point and then give you a little bit of feel for how this experiment evolved with time and how it's still evolving. Harper's inspiring simulations of 15 years ago seem to be really close to the truth. There is an M2 tidal beam propagating across the McCrary Ridge. It has something like 0.5 to 2 gigawatts of energy in it. So it's like a 20th of the energy radiating from the 1,000 kilometers of the Hawaiian Ridge. But this beam is much narrower, so its intensity is as big as they get on the planet. And it seems to survive the mesoscale in the Tasman Sea and get across and reflect, roughly 60 to 90% reflects. There's still a lot of mixing, and this coherent mix of incident, reflected, and locally generated waves, which I didn't discuss, makes for a very complicated pattern. Nothing is simple, but it's well within the range of things that local numerical models handle very well. And there are issues for you. We want to understand what the mid-water versus the seafloor mixing rates are, what causes the bores and the lee waves that are associated, that create this mixing, and what their climatology might be in the future as well. The bottom line here is that 10-kilometer scale features in the 3D nature of continental slopes matter enormously for deep mixing. There's the horizontal scale of the topography, and there's the horizontal excursion distance of a baroclinic tide, how far a particle is going to move back and forth in a tidal cycle, which is a number that can be like 10 kilometers. And so the microbathymetry of the deep sea is becoming really pretty important, and different phenomena will get tuned to dissipate as the climate changes extremely. But it turns out this microbathymetry is being mapped by people pretty much anyway, and it's something that is sobering, but it's not an intractable problem to deal with at all. Let me go through a little bit of the geopolitical scientific history of the experiment, both the real and the surreal aspects of it all. That might be of some interest. We got together to really try to do this thing 2008, 2009, which was just when the economy was crashing, if you recall. And finally got it through NSF and funded about the time that the crash had its biggest financial impact on NSF. So something was funded that was fairly bare bones. And we knew that we were not going to do a process experiment and then follow it by a modeling experiment. We needed all the help we could get very soon to figure out how to attack this place. So the modeling and the glider studies started out on day one of the program, and they confirmed that this was going to be a complicated place to work. One of the oddities of NSF is that the people who fund experiments are slightly removed from the people who pay for the ship operations, and it wasn't appreciated what a expense it was going to be to get mainstream U.S. global ship to the Southern Ocean in the summertime. And as that got expensive, any hope for a pilot cruise, which was in our proposal and accepted initially, got wiped out. And that we paid a horrible price for that. The main field program was delayed for a year by ship availability, bringing the Revell from Asia to the Southern Ocean. And that also was quite a strain on the experiment. From Eric Itzwer's point of view, he committed funds to this program at a time when he had the least funds. And so all of his cards were played, and then the program was sitting doing nothing for an extra year, so he was having nothing to show for it, and it was very, very frustrating for him. And from our point of view on our side, we had engineering teams with too little to do in 2014 who were double booked and so on in 2015, and this made for a stress all the way around. So midway along, the T-beam people turned to Schmidt, Amy Waterhouse, and Sam Kelly took the lead to try to get documentation that some beam was indeed coming across the Tasman Sea. And this made for a very interesting exercise. But Eric was able to fund Amy and Sam to lead that operation midway or late along in the experiment, and they went out and did their best. Finally, we had a field program that was really well guided by numerical modeling and reconnaissance in advance. And I think we put our resources where they really should have been. The thing was so strapped economically that it made an amazing use of volunteers. It included lots of people from the South Pacific and Australia because one didn't have to pay their plane fare. And everyone up to Sonia Legg, who was on board helping Matthew put moorings in. And deployment, the mechanical deployment of all of this stuff in the Southern Ocean went well beyond what we could expect. But after the fact, when the data came up, the McLean profilers had trouble in the Roaring Forties, and the data return from them was much worse than the people involved were accustomed to getting. So it's a little bit disappointing. Finally, thanks to the various delays, we get the instruments back in the lab and start looking at the data 3 months before the end of the formal financial program, and everything was run on funds carried forward for the last year, and now most people are beyond that, and the final analysis and archiving and so on is going on, and will continue with people getting supplemental funds from the NSF as needed or using other funds. So that's kind of a background of the thing. And we've met as recently as just a few weeks ago when people's paths crossed in La Jolla to refocus on this and look at each other's data. Now, for me, as an old geezer in the field of oceanography, there's a whole new side to what's going on that I'm totally orthogonal to, but it was necessary to have ongoing day-to-day, blow-by-blow internet presence for the experiment while at sea to support our sponsors. And in part, if we didn't, the Schmidt group on the Falkor was all about ongoing day-to-day presence, and it would make it sound as if the entire TTide experiment was funded by the Schmidt group rather than by NSF, and this got to be a sore point for our NSF sponsor. Fortunately, Matthew, Alfred, and Jonathan Nash were aware that this was going to be coming and brought along a full-time science writer on leg one of the Ravel trip, and so there were blogs going back and forth by the two ships during the course of things. And in the end, Matthew and his group escalated this whole thing in a way that I'll never forgive him for by staging a great flash dance on the fantail of the Ravel, filming at one of our students. Maddie Heyman is a gifted choreographer on the side, and she did this. And this thing went viral on the internet at a time, they were mainly worried about trying to collect data. So it was a pretty amusing thing. And of course, when I went out as a dour old fogey, we didn't do any flash dance and got back to shore, and the assistant director of Scripps' first comment was, nothing to dance about on your leg, eh, Pinkel? So it was pretty amusing because I was thinking actually that the thing went pretty well. Our presence so far, we tried to make an impact on EOS to demonstrate what the experiment was all about. And a cover article came out on EOS a year ago, and it was a new experience for me in that I published in kind of popular press-like journals for lots of different experiments. But in this particular case, the professional editorial staff, except for the senior editor who ran everything, the junior editors were in large cases out on various sorts of sick leave, and they had substitutes in. And these science writers were desperate to include terms that were buzz terms in my taste, that all in some sense sort of Freudian. And I sent in what I considered to be a very good general purpose, 3-page article on what we had done. And when it got rewritten, it wasn't to make it more accessible in style. It was to include all of the drama that the editors insisted had to be there. And the science was changed, and it was actually quite wrong. The title of the headline as it came back to me was Ocean Mixing Drives the Circulation, Ocean Turbulence Drives the Circulation of the Ocean. And it was just not the right story, but it was sensationalized so that it would sell. And we finally had it out with the senior editor, who was very understanding and let us write a more reasonable thing. But in the end, the cover picture of EOS from that year, even though the cover article was about TTide, the cover picture was a close-up of a piece of glacier. And the very first line for on the cover, melting glacier water meanders to the ocean where it plummets. You need that word. Plummets to the seafloor. And for those of us who know how hard it is to make fresh water plummet to the seafloor down in the Southern Ocean, it was pretty disheartening to see that happen. And then immediately below that was a non-edited line that is very bland by comparison, of course. At any rate, that's kind of my perception, again, is to the political and logistical background of the experiment. I think, by and large, it was a very successful effort, and it's at a spot where the money is now gone, and the satisfaction from learning stuff has yet to really peak. So it's in an awkward phase, and the challenge will be to keep the momentum up and keep us going with these data sets. We're required to get them archived both in the Australian and the U.S. system, and everyone is planning on that. But again, the thing that might be most useful to you guys is not the output of a bunch of thermometers, but the output of the MIT GCM that's tuned based on what those thermometers have told us. And the cool thing is that things like an 18.6-year cycle in eddy diffusivities and large-scale climate are showing up in various people's talks now. It's not that the tide is the dominant thing mixing the ocean, but in some areas of the ocean it's big enough that you can really track it. And so an attitude shift is happening, and at least more and more this is looking like a tractable problem. At any rate, let me stop, ask questions, ask 4 questions, and